uh, a very esteemed dear guest, distinct speakers, and quantum aspirants. Welcome to Quantum Week celebration, Alice in Quantum Land, an electrifying collaboration between Kanya Mahavidyalaya Jalandhar and Indian Association of Physics Teachers. It is with great pleasure and immense excitement. I extend my warmest greetings to each and every one of you gathered here today. Our collaboration with Indian Association of Physics Teachers, IAPT, underscores our shared commitment to fostering scientific literacy and thus promoting excellence in physics education. As a convener of this momentous event, I am deeply grateful to our esteemed speakers whose expertise and insights promise to enrich our collective understanding of quantum mechanics. Today we have with us Professor Arvind, Vice Chancellor, Punjabi University, Patiala, Professor Ajoy Ghatak, Emeritus Professor, IIT Delhi, Professor PC Deshmukh, and many more alumnaries. We are really grateful to all the guests who has joined us. I would also like to extend my heartfelt thanks to our mentors, Professor Dr. Atima Sharma Dwivedi, Principal Kanya Mahavidyalaya, Professor P.K. Aluwalia, President IAPT, Professor Jaswinder Singh, President Digital Council Set 2, and to all the members of organizing committee for their unwavering dedication and tireless efforts. Let's begin the event by taking blessings of Almighty. Light symbolizes brightness and prosperity. With this noble thought, let us start the event by virtually lighting the lamp. Shashi sir, please play the video. May the divine power bless us all as we embark on this week-long journey immersed in mysteries and marvels of quantum world. We find ourselves at the nexus of innovation and discovery. With immense pride and pleasure, I would like to let everyone know that we have received 894 registrations from 25 states for this national workshop. These include 686 students from undergrad, postgrad, and doctoral programs, along with 200 faculty members and 20 individuals from diverse backgrounds. Zoom ID details and YouTube streaming link have been shared with all participants for joining. To all our participants, I would like to add that special prizes will be given for your active participation. I encourage all the participants to immerse yourself fully in festives, engage with your peers, and seize every opportunity to expand your horizons. After every expert talk, a quiz will be shared in the chat box and it will be considered as your attendance mark. Along with this 1 week online program, we are simultaneously conducting 2 days on-campus program at Kanya Mahavidyalaya Jalandhar, where our students as well as the students from other institutes are participating and expanding their horizons through expert talks and hands-on workshop. Today, we have conducted 2 expert talks by IAPT luminaries Professor P.K. Aluwalia, President IAPT, and Professor K.N. Joshipura, former Secretary IAPT at our institute. Before moving ahead, it is my proud privilege to make you aware about my great institution having a history of 138 glorious years. Established in 1886, Kanya Mahavidyalaya is an autonomous and heritage institution. It is a premier and its own kind of institution with the proud privilege of having been visited by 5 presidents and 5 prime ministers of India. KMV has been conferred with the Star College status by Department of Biotechnology, Government of India. KMV is the only women institute of Punjab decorated with Star status grant. It is worth mentioning here that there are only 29 colleges in India and 3 in Punjab having DBT star status. KMV has been conferred with FIST and Curie grants from Department of Science and Technology, Government of India. It is the only college in Punjab designated with IAPT Anveshika Centers. KMV Jalandhar is the first and only women college in state of Punjab conferred with the autonomous status and is the first college among Guru Nanak Dev University affiliated colleges to back Kaushal Kendra. It is matter of great pride for all KMVites that under the able leadership of our head of institution, Kanya Mahavidyalaya Jalandhar has been selected among top national institution in India as per Best College Survey by India Today and adjudged number 1 as the autonomous college in Punjab by Outlook magazine. So KMV has a wide success history and I have very briefly reported the facts. Although we have not gathered in our institution physically, so let's explore the glory of this institution virtually by having this small video clip.
Vibrant, energetic campus life at KMV. We nurture young women who are confident, ambitious, and equipped with the right skills to face the challenges of life. Ideal amalgam of traditions and modernity. Education at KMV is focused on preparing global citizens who will be the leaders of tomorrow. Personal care, warm and safe environment for girls at KMV helps them to thrive, dream big, and achieve high goals in life.
Come join the winning journey at KMV. Become future ready with KMV. Be the best with the best.
fervently young girls to Kanya Mahavidyalaya, Jalandhar.
Yes, Kanya Mahavidyalaya Jalandhar is the autonomous and heritage institution, and the success story of our reputed institution cannot be completed without acknowledging the hard work, able guidance, stewardship, and continuous support of our worthy Principal Ma'am, Professor Atima Sharma Dwivedi. Now it is a time to invite our Professor Atima Sharma Dwivedi, Principal Kanya Mahavidyalaya Jalandhar, alumna of Harvard University, for her honorary remarks. Ma'am, over to you.
Thank you, Neetu, for the very kind information and also my introduction. To begin with, I would like to once again welcome all the participants to this exceptional workshop on the topic Alice in Quantum Land. This is indeed something very unique because when I saw the topic and also the participation of IAPT, that the Indian Association of Physics Teachers in this, I was extremely happy, and also the participation of students pan-India from 25 states. It was such a great motivation for all of us. I must congratulate the IAPT, its chairperson of the Northern Zone, Dr. P.K. Aluwalia and Dr. Neetu Chopra, along with the team of other brilliant people in the Department of Physics of Kanya Mahavidyalaya, to have organized such a wonderful this workshop in which the whole country comes together to learn about this. I think when it comes to quantum physics, I'm myself like an Alice in this wonderful, wonderful wonderland. I too need to learn all this. So I'm a student myself, though right now I speak as head of the institution. And I'm also very grateful to all the exceptional, the outstanding speakers. Some of them very illustrious, like I know Dr. Arvind, and there are speakers from IIT of various IITs and other professors who are going to be, joining and participating in this event. You are the ones who are making it very valuable. So I must thank all the resource persons, the speakers. I personally know Dr. Arvind, so thank you so much, and also the other speakers. Well, when it comes to physics, it's an extremely fascinating subject. Very, very fascinating for anyone to know about the universe, about what the quantum physics has to say today. So the leaps and bounds in the growth of science and technology is coming up, and we have to keep pace with that. And I'm very happy that the young people of India are interested in such subjects, because we need to build a very strong and broad base of science and technology for the mission of creating a developed nation. And India has great future, and topics like quantum physics are the future for the growth of this great nation. So it is really going to be a very important, a very valuable workshop for all of us, especially the young people. I congratulate not only the organizers, the IAPT officials, Professor Aluwalia especially, because he has personally come to our institution and giving us all the encouragement in holding this kind of a workshop. So I wish you all the best. And I hope that in days to come, this is a week-long workshop. We all will learn a lot. As I said, that I'm myself like an Alice in this wonderful, wonderful workshop. So wishing you all the best. And I hope we have very, very interesting and new revelations coming to us during this workshop. I think without saying too much, because we need to go back to the real content of the workshop. And also, I would like to say that Kanya Mahavidyalaya will always like to contribute to the development of young people. We are the pioneers of women education in this country, and we would also like to continue our role as the leaders for the development of all the good initiatives in the field of education for service to the society and to the nation, and of course, largely to humanity. So over to Dr. Neetu. While I once again congratulate you, Dr. Neetu, and
Thank you,
I
ma'am.
can see the other faculty members as well. Wish you all the best for the coming days.
Thanks a lot, ma'am, for your valuable and insightful views. You always encourage us to such a level that we go head and head. Thanks a lot, ma'am. Now it is time to invite Professor P.K. Ahluwalia, President IAPT, for his presidential remarks. With a distinguished career spanning decades, Professor Ahluwalia is luminary in the field of physics. His expertise in creating designer quantum states, particularly artificial atoms, is unparalleled. Without taking much time, I invite you, sir.
Thank you, Professor Neetu. First of all, let me welcome all the participants in this workshop who are both on the Zoom as well as on the YouTube. I'm very happy that we have with us very distinguished speaker today, Professor Arvind, who is one of the architects of the quantum initiative in the country. And it was such a joy always to listen to him and understand the depths of the subjects he picks up for sharing with young minds. So welcome, Professor Arvind, to this very special workshop. It's a new initiative of IAPT in the sense that we have tried to celebrate World Quantum Day, which is on 14th of April, with this particular workshop being conducted at Kanya Mahavidyalaya. I am very thankful to Principal Athima Sharma Dwivedi. I was with her in the morning today. We had an in-person session with the students of Kanya Mahavidyalaya today, in which I and Professor K.N. Joshipura actually initiated this quantum week. I'm also thankful to the principal that she is encouraging such initiatives in the college. I was so much pleased to be in the campus of this famous college of the country. It has a history of 138 years. That's not a small duration. It has contributed immensely in the women education, and that really makes it very special for us in the country. I visited their Hall of Fame. I visited their labs. I was really impressed by the facilities which are there and the programs which they are running. I am looking forward to, with the Professor Arvind's talk, other talks also which are going to be there in this week from our very distinguished speakers, Professor A.K. Ghatak, who is a pioneer in the country as far as quantum mechanics is concerned. He has been a passionate teacher of quantum mechanics, and he has written books which are very favorite books of the students and teachers in the country. Also, we have in this Professor P.C. Deshmukh, who is an a distinguished professor at IIT in. So what we intend to do is to bring the best brains here. Professor P.C. Deshmukh is at Tirupati, and he is also adjunct faculty at number of places. We have very close association with him also. We also are going to have a set of discussions, particularly a panel discussion, and some other lectures which will be of great interest to the participants here. And you will be hearing from people who are working in the next quantum revolution which is really exciting young people all around the world. This is a small effort of the Indian Association of Physics Teachers that we reach out to young minds, young teachers, and even public. Today's lecture, the title of that is so wonderful that you will be taken through the journey of the quantum mechanics, how it has reached the stage where it stands today, and is exciting all of us. I wish this program all the best and great time to the participants. I am thankful to the distinguished speakers of this workshop for accepting our invitation. Thank you very much.
Thank you so much, sir, for your kind words and for being a guiding light in field of quantum mechanics. We are truly honored to have had the opportunity to learn from you. Thank you so much. Once again, a big thanks to all of you for joining us during inaugural session of this 1 week event, Alice in Quantum Land. May this week be marked by enlightening sessions, fruitful collaborations, and unforgettable memories of discovery. So let's now pay our attention to Dr. Sangeeta Prashar, Assistant Professor at Kanya Mahavidyalaya, Jalandhar, who will lead the next segment of the event. So over to you, Dr. Sangeeta. Dr. Sangeeta.
Hello. Good afternoon. Am I audible?
Yes, yes, Sangeeta, please go on.
Thank you. Thank you, ma'am. Thank you very much. Good evening, ma'am. Thanks to Dr. Neetu Verma also, and to the respected online present dignitaries of IAPT and dear participants of the event. I am delighted to introduce Professor Arvind, the Vice President of Vice Chancellor of Punjabi University, Patiala, and a distinguished theoretical quantum physicist with a profound dedication to science education, science communication, and advancement of science pedagogy in Punjabi University. Currently on deputation from ISER Mohali, where he holds the position of Professor of Physics. Professor Arvind's academic journey is marked by notable achievements with a master degree from IIT Kanpur and a PhD from IISc Bangalore. He has made significant contributions to academia. Throughout his career, Professor Arvind has held various academic and administrative roles, showcasing his multifaceted expertise. Notably, he has been recognized with the INSA Medal for Young Scientists in 2000 and has been actively involved in national initiatives such as National Multi-Institutional Network Program on Quantum-Enabled Science and Technology. As a lead scientist in quantum information, he has established a prominent research group and organized international conferences, contributing significantly to the field's advancement. He has more than 70 publications in the international journals and has supervised 7 PhD students. Beyond research, Professor Arvind's passion for education is evident through his efforts in designing experiments for physics education and developing innovative pedagogical tools. Moreover, he has been a vocal advocate for educational reforms, emphasizing the integration of pure sciences with social sciences and linking science with society at all levels of education. Professor Arvind's advocacy extends to the public schools, where he actively engaged with teachers and addresses various issues in science education. In essence, Professor Arvind embodies a commitment to excellence in both academia and education, and we can count on his achievements in the field. But it seems as if I am becoming an impediment in facilitating the exchange of his viewpoints. We are privileged to have him amongst us to share his insights on quantum mechanics. Therefore, we extend our cordial invitation to Professor Arvind Dhillon to deliver a lecture on his captivating subject. Over to you, sir.
All right. Can you hear me?
Yes.
Yes,
Uh,
Dr. Arvind, I'm sorry to interrupt, but let me once again welcome you. And this is Dr. Atima Sharma. We have met in person in the college, and to have such an illustrious scientist amidst us, Vice Chancellor, sir, it's such a privilege. So once again, welcome to you, and thank you for being here on this platform.
So is my presentation visible?
Yes, sir. Visible.
Are the slides changing?
Yeah, moving, sir.
Okay, very good. So let's begin. So first of all, I'm very thankful to IAPT. See, I'm a life member of IAPT for more than 25 years. So it's always a pleasure to associate with the IAPT. I always say that any IAPT event reminds me of people like, Babulal Saraf and Khandelwal. I did not work directly with Khandelwal, but I had the privilege of working very closely and directly with Professor Saraf. So IAPT is a forum very dear to my heart, and therefore it's never a no from my side whenever IAPT wants me to get involved with any of their programs. Similarly, the KMV as a college is quite well known to me, as the principal ma'am was saying that I have met her, and also I know the entire physics faculty there because I was one of the mentors for them in the Star College program. So again, when KMV invites, I normally am not able to say no because of my close association with the faculty, particularly with Dr. Neetu Chopra, who is the organizer of this event. Anyway, let us begin. Felix Bloch, a Nobel laureate in physics, once said that don't underestimate the pleasure of listening to a talk which you actually understand, which means that most talks are not understandable and they just fly over your heads. I have been particularly careful in planning my talk in such a way that young students are able to connect with the talk, and I've kept it at a level at which they will be able to engage. And I have brought in many historical developments and left out many technicalities, which I think will get covered as other experts talk over the next week. And in any case, what I understood that this program is more towards exposure than towards actually teaching the subject. So with this, let me begin. As I've given you the title, From Quantum Mechanics to Quantum Technologies, A Journey of 100 Years. And that is the historical perspective in which I will talk. Now, it looks like that you will not be able to interrupt me and ask questions because people have been muted. So therefore, you keep your questions and we can take all your questions in the end. I will speak for about 40 minutes maybe, and then we can have an open session because I know young people will have lots of questions. At this stage, let me ask the organizers that is audio video okay? Is it fine?
Yes, sir.
All right, because otherwise I can change the levels. Good. So let us begin. So quantum revolutions, as I have put it, so the first quantum revolution happens between 1900 and 1922 or 1924. Many people put it in that bracket. So first 20 to 25 years of the 20th century. And what happens in this period is very remarkable. So since they are physics students and physics teachers, see, at the end of 19th century, physics was a very well-developed subject. So unlike many other sciences, so we had Newton's laws, we had thermodynamics, we also had Maxwell's theory of electromagnetism in terms of Maxwell equations and so on. And relativity was very much there in the Maxwell equations, but it was brought out very explicitly by Einstein. So by the in the beginning of 20th century, physicists were very proud people that they know almost everything about the world. However, lot of phenomena were found, lot of experiments were found in which could not be explained using the laws of classical physics, or I would say laws of the 19th century physics. And it's important to see what was going on. And to give you further context to it, Lord Kelvin, for example, gave a talk towards the end of 19th century where he talked about end of physics. In his talk, he even gave a list of open problems in physics, which he thought will get solved in the coming few years or decades, and we will know everything about everything. On the other hand, physicists are always skeptical people. They don't really, believe in when other physicists are saying things unless there is a good evidence. So in the laboratories, lots of things were being measured. And to give young students an example, see, you all know that matter when heated produces radiation. So hot matter emits light. So heater coil is red, it emits red light. You heat it further, the color changes, so on and so forth. So light is nothing but electromagnetic radiation, and electromagnetic radiation is produced when charges are moving or oscillating or accelerating, as we all know. So if you take a charge and hold it like this and shake it, it will produce an oscillating electric field. And that oscillating electric field will produce an oscillating magnetic field, and you will have a wave going on, and electromagnetic waves, and which include light and heat and X-rays and so on and so forth. Now the question is that heat is a very random kind of energy. So if you are having heat, which means all kinds of random motion is happening and molecules are moving in random ways, then light emitted from hot object should also be random. So you should have all colors, all frequencies, all kinds of light. But as students now, of course, in much later, about 120 years later, you know that if I heat hydrogen, I get hydrogen spectrum. If I heat neon, I get neon spectrum. If I heat sodium, I get sodium spectrum. So you typically get only a few frequencies which are characteristics of the material that you are heating. Then if heat is a very random kind of energy, why is it that the radiation which comes out of hot matter is not random, and instead it is characteristic of the material or the atom or the gas which you're heating and so on. So this is something which is very puzzling, and there is no answer in the classical physics. Now, if you move to, for example, materials, why is water liquid and why is oxygen a gas? You cannot answer this within the classical physics. Or why certain things conduct and have free charge carriers and others are insulators. Further, others are superconductors, some are semiconductors. None of these things can be understood using classical physics. So more you look around the physics phenomena that we know about, most of it is not really explainable or understandable using the classical ideas or the ideas of the 19th century physics. So this was the reason that a new set of explanation had to be evolved. And starting with the Planck's theory of radiation, where the black body radiation, how it is coming about and so on, was explained using this whole idea of a quantum or a packet of energy, and photoelectric effect, where bundles of energy are absorbed as bundles, and you cannot just have two photons together pull an electron out of a material. So photons cannot really be added to provide you a larger energy which can be used to eject electrons. You need a photon of a certain threshold energy. Most of you have seen this. So all these things were leading up to a new kind of physics where new ideas had to be introduced. And of course, then came the Bohr atom, and then came various other things. So it was towards the end of these years, 2022, 2023, 4, that we had quantum ideas put together into a framework, and that framework which we call quantum framework, which we know as quantum mechanics or quantum theory or quantum framework today. Now, as we will go along, we will see that this led to a fundamentally different way of looking at the world. And we had to completely discard some of the ideas in building this new framework. And many of these are very counterintuitive, and many of these are things which are not so easy to understand and absorb and so on. We'll come to that as we go on. So I call this as the first quantum revolution, in which quantum explanations were built. And from this quantum explanation, a framework was evolved, which we call the quantum framework. This was the birth of quantum theory. Then the second quantum revolution, which roughly begins in 1920s, and of course it's still continuing, but I have deliberately put as 1984 as not the end. I mean, this is where this revolution was most active. This is where the quantum framework was applied to various phenomena at many, many different scales. So quantum theory, which was originally invented for atomic phenomena, people found can also explain nuclear phenomena. Now, nuclei are much, much smaller than atoms. So similarly, the same theory could be applied to solids, same theory could be applied to almost anything in the world, all the way up to neutron stars. For example, when Chandrasekhar calculates the limit of stars which would explode when a supernova explosion happens, the calculation which he does involves quantum statistical mechanics, and therefore quantum ideas can be applied to objects as large as stars. Of course, so the quantum theory was applied to solids, to nuclei, to particles, and a lot of discoveries were made in this period. So this was a full half century or a century of quantum mechanics being applied. Similarly, then quantum theory was applied at different time scales. So it is a framework which till now has never been contradicted. It is valid at all time scales that we know and all length scales that we know. And if you look at the modern particle physics developments of quantum field theory, or what they call grand unified theories and unified theories, they all are part of this second quantum revolution, as we call it. And therefore, as we will go along, we will see that since so much phenomena was waiting to be understood using quantum mechanics, many of the counterintuitive aspects of quantum mechanics people did not really talk about, because they were busy applying quantum mechanics. And this was the era which, in some sense, continues even today. People are applying quantum mechanics to so many things. Then in 1984, something very interesting happened. So roughly in those years, 83, 84, people were talking about strange ideas. Well, before I talk about the third revolution, let me also tell you that while the quantum revolution was unfolding in the 20th century, another revolution also was unfolding in the 20th century, and that is the revolution of computing, or revolution of computers. In 19th century, people did not think machines to be able to calculate or compute. Whereas in 20th century, first came the theory that you could have machines which could compute, and a lot of work happened in computer science. And then, of course, by middle of 20th century, we had some kind of computers. And by the end of 20th century, we have laptops and desktops and whatever. And today, we have extremely sophisticated computing devices, even inside our mobile phones. So another revolution was happening parallelly. And this parallel revolution of information science or computing or calculations using machines was using quantum ideas in the sense of quantum properties of matter. So you needed semiconductors, you needed lasers, you needed all kinds of technologies which were coming out of the second quantum revolution. However, at the fundamental level of thought or understanding, it was based on regular ideas of logic and gates and NAND gates and all that, and no new quantum ideas were being used in the logic of these computers. So even today, all the computers that we use, they use classical logic, but quantum devices in terms of material properties of matter, which are quantum in nature. Now, what happened in 1984 was that a new communication protocol was announced by Bennett and Brassard, where they said that if you want to securely communicate with a fundamental level of security, a crypto scheme, or a completely secretive way of communication, then you will have to use quantum properties of matter, not just in terms of devices, but in terms of logic. And we will see as we go along. Then very soon, Feynman, for example, while trying to solve certain problem, came up with an idea of a computer based on spin half particles, where spin up is 0 and spin down is 1, and you can make computations of flip of bits by up spin going down spin and so on and so forth. And of course, he left it at that, saying that this was a theoretical construction and it would be extremely difficult to build such a thing. And but he did point out that if built, it could be useful in maybe solving quantum problems because it is based on quantum two-level systems. So those were the beginnings of the field. And then, of course, people like David Deutsch and so on were developing these ideas. The spirit being that at a fundamental level, can we use quantum ideas to reinvent the areas of communication and computation? So what those are, we will see as we go along. So this why I call the third quantum revolution, which begins in 84, slowly warms up, and a very, very big achievement happens in 1996 when Peter Shor comes with a quantum algorithm to solve the factorization problem, a problem which is not solvable on a regular computer. And with this, we kind of move to the third quantum revolution, which is the revolution of quantum technologies. So it's about thinking about computation, communication, and metrology. Metrology means measuring very, very small signals using fundamentally quantum ideas. So it's not a question of quantum properties of matter, it is certain aspects of quantum ways of thinking which goes into building these devices. So this is what is a century-long story which I want to tell you a little bit about in today's lecture. So to summarize, the quantum theory starts in the beginning of 20th century with what we call quantum explanations of phenomena which cannot be explained using quantum physics. In about 20-25 years, it becomes a framework, which is fully developed framework to understand the world around us. And using that framework, scientists understand all kinds of phenomena from nuclear and particle scale to solid scale to stars and so on. And that continues and even continues today. And then something very interesting happens that towards the end of 20th century, people start thinking about applying quantum ideas to revolutionize computing. And that is the revolution which we are at the amidst today. All right. So now that I have mentioned to you that the classical framework which was developed in the beginning of 20th century is very different from the way we think about nature and about word in the classical world. So what are the differences? So the first differences is that the classical word is continuous while the quantum word is discrete. So I already mentioned that, two photons cannot be added to give you a bigger photon, and they will not be able to do the job which a larger energy, bigger photons will be able to do. The charge, for example, on the electron cannot be divided into half. It either comes as one electron or it comes as two electrons. It cannot come as half electron. So there is a certain discreteness to our word. So the word is quantum. It is discrete. However, discreteness is not something that we are not able to imagine. I mean, after all, humans know how to handle discreteness. Biological sciences, living beings are always discrete. There are either 20 people in a room or there are 100 people in a room. They are never 20 and a half people in a room. Seeds, fruits, so trees, all these are discrete objects, so they can be counted. So discreteness is not something that we are not used to intuitively. Just that people felt that at a fundamental level, we should be able to divide nature endlessly. But then quantum framework tells you that that is not possible. And beyond a point, you cannot really divide things. And there are fundamental constraints on that. So that is one aspect, which of course is new and novel and very important to understand the phenomena. However, intuitively, it is not something that as humans, we don't know how to deal with. What we call is the discreteness. Now, the second is a much more counterintuitive aspect of the quantum framework, that is the superposition. So superposition principle tells you that in your classical way of imagining, if situation A is possible and situation B is also possible, then quantum mechanically A and B are possible together. Now, many times you have not been told this way, but we start teaching some of these ideas very early without talking about them. When you say that an electron is in s orbital, or you say that an electron is in p orbital, you can turn around and ask the question, electron is a particle. If it is a point particle, then how can it be in this s orbital, which is like a spherical shape, or how can it be in a p orbital, which is like a dumbbell? Where in the p orbital is the electron? Quantum theory will say no. Since electron can be in any of those places, it can also be in those places together. Now, this is a principle which is a very deep principle which we don't fully understand completely, and it has very interesting consequences. But it is true and has been verified in experiments, as we will see, and some of its consequences also we will see. For example, like if I'm giving this talk today in the IAPT workshop and I'm sitting in my office, I can't be doing something else at the same time. But in the quantum framework, it is true. I mean, there could be multiple things which could be happening at the same time, and it is not their superposition can be actually happening. Now, that superposition is like things happening at the same time, but then you can't see all of them at the same time. So it's a very subtle principle, and it takes one a long time to get used to it. But let me try to give an idea about it. The second new feature of the quantum framework is the probability, because you must have heard this quotation from Einstein that God cannot be playing dice with nature. So Einstein was very unhappy that probability is a fundamental aspect of quantum framework, and it is not just introduced to express lack of knowledge. I think this also I should spend some time explaining, because you see, in the classical world, we introduce probability to express our lack of knowledge. When I don't know something, I say probably. But then actually, there is only certainty. So when I say that, let's assume that we are in a room and I release one molecule. Now, where is that molecule? After some time, you will say it has equal probability to be anywhere in the room because it has been colliding with the gas molecule. However, it is one molecule. If it is one molecule at the back of my mind, I know that one molecule can be only in one place at a time. So I am introducing this probability of finding the particle to be equal in all parts of the room because I don't know where my molecule has gone. So it's an expression of lack of knowledge. This is how we introduce probability in the classical physics. However, if I have, say, 10 radioactive nuclei with a half-life of 10 minutes, after 10 minutes, it is quite likely that 5 will decay. Now, which 5 will decay? 1, 2, 3, 4, 5 will decay, or 1, 2, 4, 6, 8, 10 will decay, or it will be, 1, 3, 5, 7, 9 will decay. So, which exactly will decay, nobody can tell me. And it is not a question of my lack of knowledge. It is actually fundamental that in the word is probabilistic, and we know only the probability with which things will happen, and nobody knows beyond that probability, or maybe nobody can even know beyond that probability. Now, this is something which bothered Einstein, and therefore Einstein, as we will see very soon, was very critical of this aspect, and he thought that this probability should come in exactly in the way it comes in the classical physics, as a way to express lack of knowledge. And behind this layer of probability, there should be a layer of certainty. But then, as we will see, that latest developments in quantum mechanics and in experiments tell you that probability has to be accepted as a fundamental object and not as something which we introduce to understand lack of knowledge, and then we can always move to a layer of certainty. The third major change in the point of view in the quantum framework is that there is no passive gathering of information. So if you see, how do you learn about a system? You go make a measurement. I want to read a book, I go read the book. That's like making a measurement on the book. I want to measure the electric field, I put a test charge and I measure the force on the test charge. Now, in all these, we assume implicitly that the object we are studying or gathering information about does not change. Why? Because we say, okay, if I put in a test charge and that disturbs things, I will put a smaller test charge. So I will say I will put an infinitesimally small test charge. And in the classical world, this is the understanding. Since there is no limit to making a smaller and smaller test charge, so I can always learn things without disturbing them. Whereas in the quantum framework, every attempt to learn about a system disturbs the system. And if you measure too many things, if you ask too many questions, you may begin to lose information that you gained from the previous measurements. I mean, to give you an example, let's ask the electron a question where you are. So electron raises its hand somewhere, I'm here. All right, so electron is here. Now I ask this electron, what is your momentum? So it gives me some value, P equal to something. Then I ask where you are. Now, since it's a quantum particle, you asked where it was here. Then you asked momentum. Then you learned that. Second time when you ask where you are, it may actually go here. So you see, what you learn by making one measurement might actually be lost. That information may not be relevant if you have asked another question. So this is a very, very interesting aspect of quantum physics, which makes it very different from the classical world, in which you can always learn without disturbing, whereas there is no passive gathering of information. So I like to give this example that if there's a quantum book, if I read it and put it back in the library, when you issue the book, since I've read the book, second time somebody reads the book would have changed. So every time somebody reads the book is different. And more people read the book, they all leave their impressions on the book, which get coded into the book if it is a quantum book. And that's a fundamental aspect. You can't really reduce the signature you leave. More you learn, more a signature you leave on the book. That's a very fascinating interplay between making a measurement, learning something, and leaving a mark of the learner on the object. So subject-object interactions in the quantum world are quite different, and they are two-way interactions compared to one-way interactions in the classical world. So lastly, I would say that the space of description in the quantum framework, which is a complex linear vector space, is very different from the actual space in which phenomena happens. So phenomena happens in three-dimensional real Euclidean space, whereas the quantum theory, quantum framework uses to represent that phenomena in a multidimensional complex linear vector space. So which means it's a meta theory, it's a meta framework in which you first map your problem into a different space, do mathematics in that space, and the consequences which you see in that space are brought back to the actual laboratory where you verify it. So these are some of the new features of the quantum framework, which was developed in the 20th century, in the beginning 25 years of the 20th century, which is now a well-established theory or a framework. I mean, many of you would have done courses in quantum mechanics in which all these you would have been taught, but now, since these things are not mentioned in this way, you can begin to see what I'm saying through the courses that you have done in quantum mechanics. Or if you're not done courses in the quantum mechanics, you see this is what you will see when you learn quantum mechanics. So either way, whatever level you are at, it's important to know that quantum framework is very different from the classical framework. Now, three features of quantum physics are extremely important for us in today's talk. So one I've already talked about, that is superposition, which means if two things are possible, one by one, their superposition is also allowed and possible. Second is measurement, which I just now explained to you, that there are no one-way interactions. Any attempt to learn about a system makes you have to interact with the system, and therefore you disturb the system, you leave some mark on the system. And the third one is quantum entanglement, which is a rather subtle concept. I will actually spend some time explaining that to you because that is fundamental for the kind of things that are happening today in quantum technologies. And what is quantum entanglement? So I have been trying to see how to put quantum entanglement in a non-technical way. So I found a way recently, and I will use that as a way to tell you what quantum entanglement means. Say things are correlated. Now, correlation is not entanglement because correlations we see in our life. So, for example, if there are twins, let's imagine there are identical twins. Now, identical twins will have same DNA, which means their DNA sequence will correlate completely. Now, this doesn't require them to, talk to each other. They have a DNA which is same because they're identical twins, because they shared the same egg which is divided into two. So they have a common origin. So that is called a common cause. So their DNA is same because it is a copy from a single DNA, which originally was the fertilized egg in the mother's womb. Now let's go a little further. So identical twins normally go to same school, they have same parents. People also make them wear same clothes. They have the same books. They go to same class. Even if they go for a movie, they will go together. Many people say they even fall sick together, quite likely, because if one gets cold, other will get cold. So most of their activities are correlated because they are now living together and they have the same environment. So if you see one of them in a cinema hall, it is very likely that other one also will be there because what else? They will go together. Because they're same home, same DNA, same health, same clothes, same school, everything is same. So this is not at all surprising. So this is regular correlation as we understand correlated phenomena. So identical twins are highly correlated, not in terms of only their physical features and DNA, they also highly correlated in terms of their activities by the virtue of the fact that they stay in the same space, do same kinds of things. Now imagine that these two identical twins separate. They separate in the sense that one is lost and now lives in another city, and there is no communication between the two. So now they were identical twins, they were together up to some age, then they separate. Very good. Now, even if they have been separated for years, they are going to look similar. Good. Their DNA also will be same. However, now they go to different school, they have different friends, they have different interactions, and there's no phone, they cannot talk to each other, they have lost touch. There is no reason that one day, if one of them goes to a first show of a film in his city, then the other one in his city will also end up seeing the first show of the same film on the same day. There is no such reason. There is no such correlation is not expected. But if they are quantum mechanically entangled particles, this is the kind of correlations you begin to observe, which you have no way to predict classically. So so for example, what would lead to this correlation? If they had a cell phone, they can talk to each other. They will say, since they are identical twins, they lived several years together, they would talk to each other and say, oh, I am going for this film, you also go for that film. In the classical world, you will require them to talk to each other, then of course they can make appointments. But if they're not able to talk, each one is spontaneously choosing the show. But so each one is making a choice, but they always end up making the same choice because they are quantum mechanically entangled. So this kind of correlations, which would require communication, can happen without communication in quantum mechanics. And this is a very, very non-trivial concept. And this is what leads to all kinds of interesting phenomena in the quantum world. So really speaking, this was the content that I wanted to explain in this talk as a way the quantum word is different from the classical word. And now I want to take you, whatever about 10-15 minutes I have left, I want to take you through a certain journey, which is basically based on the things which I told you in this half an hour. So Einstein was unhappy with this whole idea of probabilities. So he thought that he wrote a paper along with Podolsky and Rosen, which is called the EPR paper. In the EPR paper, he argued that quantum mechanics is incomplete. It may be true, he said, but it is incomplete, which means that we need a better theory than quantum mechanics, which will not have probability, which will have certainty. And he wrote a paper in which he showed, in his own way, he proved that quantum mechanics is incomplete and we should go beyond quantum mechanics, develop a new theory which is better than quantum mechanics, which when averaged over should become quantum mechanics. So those are called local hidden variable theories, in which you have specific outcomes at the level of hidden variables, which becomes quantum mechanics when you integrate over the hidden variable. So that is the kind of Einstein, being Einstein, was able to argue this very well in this paper. And many people who thought that Einstein was right started developing such a framework which was better than quantum mechanics, which becomes quantum mechanics when averaged over those hidden variables. However, this happened in 1935. So Einstein wrote this paper about 10 years after quantum mechanics was fully developed. And then people started looking for this framework which is better than quantum mechanics, new theories, and so on. But there was no success. Nobody could find such a framework, and the field remained where it was. And also, as I told you, that most people in those years were busy trying to apply quantum mechanics to newer and newer phenomena. Not many people really bothered about this fundamental issue, whether there should be probability or whether you should have something deeper than quantum mechanics, because consequences of quantum mechanics itself was not fully explored, and people were busy applying quantum mechanics to various phenomena. Then came the fundamental work of John Bell. What John Bell did was he was a very interesting personality. I mean, he wrote only about 10, 11 papers in his own whole life, and was a very deep thinker. So he inverted the problem. Instead of looking for a model better than quantum theory following Einstein, he asked a question: what if such a model exists? So let's assume that somebody has found a theory better and deeper than quantum mechanics. Let's assume such a theory exists. What will be its consequences? So he proved a theorem called Bell's theorem, in which he showed that such a theory may be true or not true, but cannot be consistent with quantum mechanics. So what Einstein's idea that we will have a theory deeper than quantum physics, and then it will become quantum physics when averaged over the hidden variables, Bell proved that that is not possible. If you develop a local hidden variable model, which is not based on probabilities, but based on actual outcomes, when averaged over those outcomes, you will get correlations which will contradict quantum mechanics. So that is his famous Bell's inequality or Bell's theorem, which basically shows that either quantum mechanics is incomplete and wrong, or it is complete and right. So that was a very interesting piece of work that he, purely by mathematical analysis, by proving a theorem, he put forward two possibilities in front of physicists, that either you discard quantum mechanics, nature will discard quantum mechanics, which means there will be experimental situations which will prove quantum mechanics to be wrong, or you accept it as a complete description and don't look for deeper descriptions based on the kind of things which Einstein had in mind. So this was a very, very fundamental work. And of course, this put the ball back in the court of experimentalists, because now one had to think of situations in which this contradiction between Einsteinian models and quantum mechanics will show up. And then these experiments will tell whether quantum mechanics is right and complete, or quantum mechanics is wrong and incomplete. So this is where the field was in 1964. All right. So then what happened after this? Things had to wait a few years. It was in 1972 that Clauser did some basic experiments in this direction. And his preliminary experiments published in 1972 showed that Einsteinian thinking may not work. Quantum mechanics may actually be right. But these experiments were rather preliminary and therefore only were an indicator that quantum mechanics might be right or right and complete, and Einsteinian thinking may be flawed. Then came Alan Aspe, who did further experiments in early 80s, 81, 82, he published papers in which he further improved the experiments done by John Clauser, and he could show that quantum mechanics is right and Einsteinian thinking about a deeper theory better than quantum mechanics and averaging into quantum mechanics looks to be wrong. But still, these experiments did not nail the things fully. So then came Zeilinger, who did a large number of experiments which showed that quantum mechanics works perfectly, while the hidden variable models based on Einsteinian logic do not work out. So nature seems to prefer quantum mechanics, a quantum framework with all its non-trivial
Start.
and,
में करना आपने कैसे on पे
counterintuitive. Some mic is on. Anyway, some counterintuitive aspects. And that's why these three gentlemen got Nobel Prize in Physics in 22. Of course, if John Bell was alive, he would have also shared the Nobel Prize. And another person who
Sir, sorry for the interruption. You are muted.
okay, now can you hear me? You muted me. Anyway.
Yes, sir.
All right. So I don't know where you. So yeah. So these three gentlemen got the Nobel Prize in 22, and of course Bell, if he was alive, would have shared this prize. Another person which did a very large number of experiments in the same direction was Mendel, but Mendel unfortunately passed away, and since Nobel Prize is not given posthumously, so he was also not part of this list. However, in the process of doing these experiments, we learned a lot about nature. And what is at the heart of these experiments is actually generating quantum entanglement, which I talked about, a very strange kind of quantum correlation, which does not exist at the classical level. So this also needed a lot of technology development and so on. So now all this, what we have learned that quantum framework is actually correct, and experiments which show that quantum mechanics is complete and right, and it has aspects like superposition and entanglement and measurement unfolding in a certain way, can actually be used to do things which we cannot do otherwise. So that is what has led to quantum computation or building of quantum computers. So Shores showed that using non-trivial counterintuitive quantum ideas, you can think about factorizing large numbers in polynomial time. So on a classical computer, it's an exponentially difficult problem to do this, whereas on a quantum computer, you can do it in a polynomial time. What exactly that means, I will not get into the details because my time is kind of running out. But if there's a question in the response of a question, I can explain this further. Similarly, Grover, Love Grover, an Indian origin scientist, showed that you can use quantum computers to search unstructured databases in times which are square root of the times needed on a classical computer. So these were two very important discoveries, construction of these algorithms, which showed that quantum computers, which are built on ideas from the counterintuitive aspects of quantum mechanics, which require entanglement and superposition, and the kind of experiments which Clauser and Aspe and Zeilinger did, you could actually build such machines. Similarly, if you want to do secure communication, see, a classical channel can always be tapped into. So no classical communication channel is fundamentally secure because you can just copy and put back the signal. And once you have a copy, on the copy, you can run computers to learn what two people are talking about. So there is passive learning possible in the classical world. Whereas a quantum solution to the crypto problem is there, where you generate entangled states and send one partner to Alice, other partner to Bob. And this way they can have shared randomness. The kind of thing I was talking about, that if they're twins, which are quantum mechanically entangled, without talking to each other, also they will end up going to the same cinema theater on the same day. And therefore, without communicating, they are correlated. And therefore, there's no third person who can know what is going on. If once they know they are entangled, one goes to a movie theater, he knows that what the other twin is doing intuitively, even without communicating with the other twin. So this can actually be shown in the experiments, the kind Aaron Aspe did, or the kind of experiments which Zellinger did. So since such correlations exist, they can be used to do secure communication, which is called quantum cryptography. So those are called quantum key distribution protocols. So quantum technologies have three major aspects. One is, of course, quantum communication, which I just now told you, quantum computing, which I told you on the previous slide, and third one is quantum sensors. So this is actually a field which is even older than the first two. So in the early 1980s, Carlton Caves and Kip Thorne, they wrote papers where they showed that if you want to detect gravity waves, as you know, are very, very mild, very, very low energy and low amplitude. So to measure or to detect gravity waves, you can use the Michelson kind of an interferometer. And then they showed that if you use quantum light inside a Michelson interferometer, the efficiency increases. And that was the first quantum sensor that people ever thought of. Now, of course, we have these nitrogen vacancies where you have a single nitrogen vacancy inside a diamond, and that can detect very, very small magnetic fields because of its quantum aspects. So quantum sensors are quantum devices which can detect extremely small signals not possible to be detected using classical devices. Quantum computers are the devices which can solve problems which cannot be solved using regular computers, and quantum communication devices are protocols through which you can do fundamentally secure communication, which means nobody can really, even in principle, learn what you are communicating. So this is a very, very fascinating set of things which now people are thinking of building. So, well, quantum communication devices have already been built and they are even available commercially. Quantum computers, people are talking about, as you know, Google, IBM, they have some prototypes with a certain number of qubits, and people are trying to get to better and better quantum computers. Quantum sensors, already some are there, and people are thinking that this is going to revolutionize sensing. Many people feel quantum sensors will revolutionize, for example, medical diagnostics, because you will be able to sense signals from human body without really any invasive way, just putting a quantum detector close to the body part that you are talking about. So already you see MRI is not a directly quantum technique, but it has involvement of spins and flipping of spins inside your body, and learning those signals by the magnetic fields which are produced by these spins. So this could become a quantum MRI tomorrow and so on. So that's why one says that in 21st century, these quantum technologies are really going to develop and take over. And what kind of quantum systems people are exploring to build quantum technologies? People are thinking about superconducting quantum qubits, which are the superconducting devices which have two states. One is up, one is down, and you could create superpositions and so on. People are talking about photonic qubits, where you have photons and quantum properties of photons. Then there are ion traps, where you take a single ion and trap it, and then you have several of them which can talk to each other as quantum devices. People are also talking about semiconductor qubits and nuclear magnetic resonance kind of systems where spins inside molecules can be used. So a lot of interesting things have happened in the past 25-30 years in this direction. And in India, for example, it's important to know what is happening in our country. So there was the DST set up this huge program about in 2019 called Quest, Quantum Enabled Science and Technology. I was very strongly involved with this program. So there were 4 verticals in this program. quantum communication with photons, where I was the national coordinator. Then, of course, there was quantum information processing with NMR centers and NV centers, QIP with ion traps, QIP with the superconducting qubits. So there were four programs under this umbrella, and they have now wound up and they have done very well to do a lot of groundwork for development of quantum science and technology in the country. And now the National Quantum Mission is being launched, has already been launched, and lot of activity you will see in the coming years to in this area. Earlier, they were calling it NMQTA, National Missions on Quantum Technologies and Applications. Then they found that this is too long a name, so now it's called National Quantum Mission. So this is already launched. I was part of the drafting of the detailed project report for this, and now some people, lots of people are coming forward to develop quantum technologies in the country. So just to tease you a bit, the Quest Theme 1, which I headed, had PIs which were distributed in this way in the country. So you can see that the entire country, the laboratories and scientists were involved in this process. So I think my time of 45 minutes is over. So let me summarize. I took you through a journey where I talked about the birth of quantum ideas in the beginning of 20th century and how it became a framework in the first 25 years of 20th century, how most of 20th century saw developments of applications of quantum mechanics and quantum framework to phenomena at different length scales and time scales and mass scales. And it has been one of the most successful constructions of human mind, the quantum framework. On the other hand, along with this development of this quantum framework, there are some inherent counterintuitive notions which we have to accept once we accept quantum framework. And those are superposition, measurement, and entanglement, which if once you accept as fundamental notions of the world around us, lead to new ways of imagining the world and new properties which are not possible in the classical world. And now we are at an exciting juncture where these new properties are being used to generate new technologies. So that is the revolution we are living through and which is expected to unfold over the coming 10, 20, 30, 40 years. So thank you for your attention. I stop here. Back to organizers.
Yes, Dr. Sangeeta.
Sir, it is almost, there are almost 10 to 15 questions asked by different persons attending the seminar. The first one is from Hemant. The question is, sir, by the current scenario, which of the following theories support the quantum world? Is it string theory or the quantum loop theory?
Well, we are not, see, string theory and quantum leap theory are somewhat speculative ideas because no experiments can tell you as yet whether they are right or wrong. So that is not what we are talking about here. In the process of trying to find fundamental quantum theories, I mean, string theory is also quantum theory, loop theory is also quantum theory. Point is that whatever string theory and quantum loop theory are talking about currently are not verifiable experimentally. So there is no way to say is that direction right or wrong.
Hope, Hemant sir, you have got your answer. Next question is from some name is Let's Go, but I think it's not her actual name. The question is, dual slit experiment with electrons one by one also shows interference. Can this be explained by quantum entanglement?
Well, quantum superposition. So it can be explained using quantum superposition. You really don't need entanglement to explain the double slit interference. It's a one level less counterintuitive than quantum entanglement.
Okay. So next question is, what if we think that three similar particles follow the 3-star model similar to a star. If we consider these three particles are entangled, then is it possible to find out position of a particle?
Yeah, I mean, if they're entangled, then they will have the kind of correlations that I was talking about. So one will have to think of a specific entangled state. And for example, if they are in a three particles, so if they're in a GHZ state, then if one is up, other two will also be up. If one is down, other two will also be down. So they will have these non-trivial three-body correlations.
Okay, hope sirs you have got your answer again. Next question is, entanglement violates general, does entanglement violates general theory of relativity?
Well, that's a good question. Actually, general theory of relativity and entanglement have not yet been combined because we don't have a quantum theory of gravity as yet. But per se, entanglement does not violate general theory of relativity. You can think about curved space-time, which comes from the solutions of classical general relativity equations. And in that framework of curved space-time, you can think about entangled states. So, as per se, quantum entanglement does not violate general theory of relativity, although we don't have a quantum theory of gravity as yet.
Okay. Sir, next question is, how does a photon accelerate to the light speed so quickly?
Photon always moves with light speed as soon as it is emitted, so it doesn't accelerate to light speed. So that's how nature is. As soon as photon is born, it begins to move with the speed of light.
So next question is there any strict boundary where particles drop their classical properties and show quantum properties?
That's a very good question. People have been trying to think of this boundary in terms of mass, in terms of scale, in terms of number of particles, but it is not yet clear fully. It's a matter of topic of research, how classicality emerges from the quantum world. So to ask this question even more sharply, one can say that if everything is quantum, how does thing become classical? That's something which we, to some extent, we know because of dissipative phenomena, because of unavoidable interactions, but not fully understood.
So I
Actually,
think
in some
student.
sense, this is one of the main issues in building quantum computers, how to keep things quantum. Because when the system begins to grow in size, they tend to become classical because of unavoidable interactions with the environment and so on. So some people do believe that classicality emerges because of unavoidable interactions with the environment. But that's not fully established.
So there is a question, can we untangle two particles just like we separate two twins?
Well, even if you separate those two particles and put them in different places, that doesn't kill quantum entanglement. Of course, there are ways and means of killing quantum entanglement, but just separation does not. That is the whole point. That classically correlated twins can be separated by just putting them in two different places, whereas quantum entangled particles, putting them in two different places does not remove the entanglement. You have to do something else.
Okay. Good evening, sir. Can we have quantum entanglement in physical properties? If
Yes.
yes, then can we determine the movement of an electron with the help of another electron which are in quantum entanglement?
Yes.
I think, sir, there are a lot of questions that could not be answered in
I
such
think
a
we can
short time.
stop here and well, it's good to have questions, and I suggest that the participants should kind of explore their questions. It's more important to ask questions and it's good to find answers yourself than to get the answers from someone. Thank you.
Thank you. Thank you, sir. Thank you very much. I want to extend my sincere gratitude for Professor Arvind captivating presentation on the history of quantum mechanics, specifically your insights into the informative eras of evolution or of our understanding of the quantum realm and its profound implications on various systems and scales. The simplified explanations of the phenomena of quantum entanglement, articulating the complexities in layman terms, was truly enlightening. Moreover, your explanation of the applications of quantum mechanics from 1922 to 1984, spanning across diverse fields such as semiconductor devices, underscore the far-reaching impact of quantum theory on technological advancements. I'm deeply appreciative of the depth of knowledge and passion you brought to the subject matter. Thank you. Thank you very much, sir, once again. Now I wish to invite Dr. Uttara. She is a head of Department of Physics, DDG, D. Vaishnav College, Chennai. She is going to, Dr. Uttara, are you there?
Yes, I'm there.
Okay, thank you, sir. Ma'am, she is going to get
Yes, ma'am.
sorry, Uttara.
Yeah, that's okay.
Dr. Uttara is
No
going
issues.
to
Thank you, thank you.
share details. Dr.
Yes.
Uttara is going to share the details of open book quiz that will be there for the 1 week. So over to you, Dr. Uttara.
Thank you, ma'am. It's really a big privilege to be in Professor Arvind's talk, and especially like a child, I'm somewhere else in a going in a time travel and a bus journey. You are now asking me to jump somewhere else. But anyway, thank you, and it's a great privilege to be associated with IAPT as such, and with IAPT RC not to in order to host this during this national seminar on Alice in the Wonderland. RC13, IAPT RC13, that is Tamil Nadu and Pondicherry, we are hosting, along with RC Not to, a journey into the world of quantum mechanics. It's an online quiz. Dear participants, we will, in few seconds, we will share the link with you. It is not going to test you. Instead, it is going to, give you, the pleasure of learning more and more about quantum mechanics. How? Because this online questionnaire itself will have small booklets. It is not going to be very difficult. You will really enjoy because it will have master followings and then picture oriented and about the scientists, literally the history. Just now we heard, you will have a bit of history here also and a lot of pictorial quiz. So actually per day, 60 members can only get the certificate. So in case you do not get certificate on a particular day, you will be definitely getting on the next day. So for 1 week, that is from today onwards till 14th of this month, this open book quiz will be open. Anybody can attempt. It is definitely to kindle your curiosity and make you learn more about quantum mechanics. Thank you, Professor Neetu. Thank you, IAPT, and thank you, RC Not to, for giving you this opportunity. Now we'll share this link in Zoom as well as in the YouTube.
Sure.
Thank you all.
So thank you, Arvind sir, for making this event remarkable. Thanks to everyone. Dr. Uttara, do you want to say it's over? We can share this link in the group as well as, so you can personally share this link with me. I will share in the student group as well as I will share them with a mail, so that it will be accessible to everyone.
Thank you, ma'am.
Right. So once again, thanks to all.